So thank you for the introduction. So today I'm going to talk about how we drive the micro-LEDs through TFTs in backplanes. And this refers more to larger area substrates rather than for AR-type applications. So this is more for kind of ultimately towards sort of TV sizes in the future, but maybe starting off kind of tablet size in the first place. Yeah, I'm Simon Ogier, CTO of Smartkem. Smartkem is a US-based company listed on NASDAQ, but it's a 100% owner of Smartkem Limited, which is UK-based. So we have our R&D in Manchester, in the north of England, and then some device development in Sedgefield near Durham, which is home to a kind of clean room facility for us to make prototypes. We also have a team of 4 engineers in Taiwan, in Hsinchu, and they work within the ITRI facility for taking our processes and then scaling it up to Gen 2.5 size for making some higher quality and larger area demonstrators. So the company makes materials. We're a materials company. We make organic semiconductors, dielectrics, surface treatment layers, interlayer dielectrics, and these are all built into a stack of materials to make a thin film transistor, used in conjunction with sputtered electrodes for the source drain and gate, and using photolithography, wet chemical etching, and dry etching to pattern them. So the semiconductors themselves, if you compare them with existing inorganic materials, have a mobility of around 2 to 3 in short channel devices, which is higher than amorphous silicon, but lower than oxide TFTs and much lower than LTPS TFTs. This shows some of the transfer characteristics of the TFTs, typical to devices. So we're trying to optimize the uniformity, very low off currents for power saving, as well as getting a good, reasonable mobility for driving current. One of the key features of our materials is that they are processed at a very low temperature, even as low as 80 degrees Celsius. And so the importance of this is that we're very compatible with a wide range of plastic substrates, whereas other TFT technologies generally require a very high temperature process for the PCVD nitride. LTPS is shown here as over 300, but typically it can be over 450 degrees C. And this has the effect of causing substrates to become yellow through the heat treatment process. Even colorless polyimide doesn't survive completely colorless after the processing. And so that's why people are interested in OTFT for making very transparent, flexible displays. But also there are some other features which I'll explain in this presentation, which is how we can actually process the TFTs on top of other devices rather than before them, which you would normally have to do with other TFT technologies. We've developed all these to be relatively easily fit onto existing amorphous silicon lines, so you don't have to reinvest in new fabrication equipment. Essentially what you'll need to do is to just increase the number of spin coaters because they're liquid coatable materials. So this shows some of the facilities within the UK we do for prototyping, and so a lot of the demonstrators that you'll see in this presentation are made within this facility, but we're now transferring more of this activity to Taiwan. So the process shown here uses a number of photolithography process steps, including wet etching, dry etching. We put down electrodes like backgate metal, source drain metal, gate metal, pattern all these by photolithography and wet etching. We do some dry etching using reactive ion etching to pattern the organic materials and the passivation layers, and again, other interconnect metals. And then we can add other layers in order to turn them into different types of devices, like OLED backplane, organic photodetectors, or logic devices. In this presentation, I'll highlight the way in which we're actually processing these as a backplane on top of the micro-LEDs rather than before them, and seeing how some advantage of those might be derived by reversing the process. Preaching to a lot of people here who already know the benefits of micro-LED, I think the main feature, especially for the large area displays, is being able to get a high brightness and efficiency in a very small area. So for instance, things like transparent displays, you'd need to have a very small area of light emission, which will be at high brightness, and micro LEDs allow